The method of moments in curve fitting is rather a direct substitution strategy in identifying the function of a specific dataset. Learn the procedure here in numerical solutions to see problems. In the method of moments, the actual moment taken from the dataset must coincide with the theoretical computation of the function, which uses integration. The first moment is then equating the actual h with the summation of y with the theoretical moment of the integral of the function of x. The second moment is also generated with the same concept, equating h with the summation of xy with the integral of x times the function of x. If you analyze these two equations, you would find a pattern that for the first moment is just multiplied by x to have the second moment. Thus, the third moment can be taken just the same, having h times the summation of x squared with y as equal to the integral of the square of x times the function of x. Now, what are these moments? They are actually the equations provided to look for the variables in curve fitting. In case of looking for the best fit line, which follows the format of y is equal to ax plus b, the first two moments will be used to provide for the two equations for the two unknowns a and b. The example in this video has 8 data points, and we are to find the best fit line using method of moments. First is to check if the method can be applied, and that is by checking the x interval. Since the moments require h, this means that a method can only work if the x interval is regular. So in this example, check that 6 less 2, 10 minus 6, 14 less 10, and so on provide a regular interval of 4. This shows that we can apply the method of moments. Looking for the best fit line, we have to use the first two moments. The first is starting with h times the summation of y, and the second having h times the summation of xy. All we needed to do now is to identify the values of each parameter in both equations. After knowing h to be 4, we can then move to the summation of y, which can be taken from the dataset, and adding all y values, we get 458.06. The next parameter comes from the second moment with h times the summation of xy, which means we needed to multiply the two data points. 2 and 15.62 provide 31.24. 6 and 28.54 give 171.24. There is also 364.5 from 10 times 36.45. Then 14 of 48.16 is 674.24, and so on for the rest of the dataset, providing 1,119.06, 1,691.36, 2,346.24, and 3,000. What we needed from these values is their summation, which turns out to be 9,397.88. At this point, we have exhausted the dataset for the actual moment. Also from the dataset, we can take the limits for the theoretical moments. Starting with the lower limit, take the lowest x value, which is 2. Then subtract half of h. The lower limit is then 2 less half of 4, which makes 0. The upper limit uses the upper x value of 30, then add half of the x interval, which makes 32. These are all the values we can extract from the dataset. Next is to place all known values into the moments. From the first moment, place h of 4 and summation of y as 458.06. The theoretical moment also would have a lower limit of 0 and upper limit of 32. Let's then delve further with the right side of the function. With curve fitting, it has been introduced that the function of x is actually ax plus b. Thus, the moment turns as 1832.24 as equal to the integral of ax plus b. If the integrand is distributed, we have 1832.24 as equal to the constant a times the integral of x dx. Then add the constant b with the integral of dx. Making them simpler, we can go ahead and integrate. The integral of x dx is x squared upon 2. Then the integral of dx is x. These two simplified integrals have the limits from 0 to 32. So to take the coefficients, we get 1832.24 as equal to a with half of the square of the upper less the square of the lower limits. Add to this b times 32 minus 0. The first moment is then 1832.24 as equal to 512a plus 32b. Generate the second equation from the second moment. The left side has 4 times 9397.88, and this is equated with the integral of x times f of x with the limits from 0 to 32. The function of x is ax plus b, so the second moment becomes 37,591.52 as equal to the integral of x times ax plus b. Distribute the integral and have 37,591.52 as equal to a with the integral of x squared plus b with the integral of x. Take out the integrand and have 37,591.52 as equal to a with the cube of x upon 3 plus b times half of x squared. Both these terms are solved with the limits of 0 to 32. So eliminate x with the use of limits to have 37,591.52 as a times a third of 32 cubed minus 0 cubed plus b times half of 32 squared minus 0 squared. Simplify this and get 37,591.52 equated to 10,922.6667a plus 512b. Then we have the two equations to solve for a and b. All we needed to do now is to plug the two equations in a scientific calculator to solve for variables a and b simultaneously. But for discussion in this video, we solve it manually using elimination. We eliminate b, so multiply the first equation by 16 and get 29,315.84 as equal to 8,192a plus 512b. Subtract the second equation. Then have negative 8,275.68 on the left. For the terms with a, the simplified coefficient is negative 2,730.6667. Thus a is then 3.0306. Plug this value of a into the first equation in order to have 1,832.24 as equal to 512 of 3.0306 plus 32b. The equation is simplified as 280.5728 as equal to 32b. So b is 8.7679. So the best fit line for the dataset is y as equal to 3.0306x plus 8.7679.